The oldest light in the universe is trying to tell us something. This faint glow, known as the cosmic microwave background, is the cooled remnant of the Big Bang's first fire. It fills the entire sky, a cosmic fossil from a time before stars or galaxies even existed. By the end of this journey, you will understand how this ancient light reveals 50 profound secrets that challenge our most fundamental ideas about reality. Why does the afterglow look the same in every direction when it should not? What hidden force could have stretched the infant cosmos to perfection? We are about to decode the universe's oldest message, a story written in the cold and the hot of the cosmic background. Are you ready to hear what it has to say? This uniformity presents our first great cosmic mystery. The temperature of this ancient light is nearly identical in every single direction we look. Every patch of the sky, no matter where we point our telescopes, glows with the same precise chill. This seems logical at first, a simple leftover from a uniform beginning. But the math tells a different story, a story of cosmic solitude. The problem is the speed of light itself, the universe's ultimate speed limit. For two objects to influence each other, for heat to even out, information must travel between them. In the very early universe, there simply was not enough time for light to travel from one distant region to another. These regions were beyond each other's cosmic horizons, forever isolated, never able to exchange a single whisper of energy. And yet, they somehow agreed on the exact same temperature, to within 1 part in 100,000. It is as if you and a complete stranger on the opposite side of the planet, with no communication, decided to wear the exact same outfit today, down to the matching socks. The odds are astronomically impossible. This is the horizon problem, and it suggests that our standard story of the Big Bang is fundamentally incomplete. Something must have connected these distant realms, something that acted faster than light itself, forcing the entire infant cosmos into a state of perfect, synchronized harmony. This perfect synchronization is not the only thing missing from our cosmic inventory. Our most ambitious theories of physics predict that the universe should be filled with strange, singular objects called magnetic monopoles. Think of a simple bar magnet which always has both a north and a south pole. A magnetic monopole would be a fundamental particle that is just a north pole or just a south pole all by itself. Grand unified theories which attempt to weave the fundamental forces of nature into a single tapestry insist that these exotic particles must have been forged in the unimaginable heat of the very first moments after the Big Bang. They should be as common and persistent as protons littering the cosmos in vast numbers. Yet, after decades of searching with the most sensitive detectors ever built, we have found exactly zero. Not a single one. Their total absence is a deafening silence. This is the monopole problem, and it points to a universe that was somehow cleansed of its primordial relics. The conditions that would have created a monopole-filled cosmos would have also left a dramatically different imprint on the cosmic microwave background, one we simply do not see. So where did they all go? The same solution that fixes the horizon problem sweeps this one clean as well. A brief but stupendous period of cosmic inflation would have stretched the fabric of space itself so rapidly and so drastically that any primordial monopoles would have been diluted to virtually nothing. It is like taking a single drop of ink and dispersing it throughout the entire ocean. The ink molecules are still technically there, but finding one becomes an impossible task. Inflation scattered these would-be fossils so completely that they effectively vanished from our observable universe, leaving behind only the smooth, uniform afterglow we observe today. But if inflation is the answer, it forces us to ask an even more profound question. What could possibly possess the empty vacuum of space to suddenly erupt with such ferocious, reality-stretching energy? This perfect flatness presents yet another profound puzzle, one that strikes at the very geometry of our reality. the cosmic microwave background provides the most precise measurement ever of the universe's shape, and the result is startling. Our universe is geometrically flat to an almost unbelievable degree. Think of this flatness not as a two-dimensional sheet, but as the overall curvature of space itself. Space could have been positively curved, folding back on itself like the surface of a sphere, or negatively curved, splaying outwards like a saddle. Instead, the measurements show it is perfectly, exquisitely flat, just like a vast, endless plane. This sounds simple, but it is a condition of unbelievable fragility. To understand why, picture trying to balance the sharpest pencil you can imagine, perfectly upright on its tip. For a single, fleeting moment, you might succeed, but the slightest breath of air, the tiniest vibration, and it will topple over. Now, imagine you came back after 14 billion years to find that pencil still standing, perfectly balanced, without having moved a fraction of a millimeter. That is the level of fine-tuning we are talking about with the flatness of the universe. For the cosmos to be as flat as we see it today, its density in the first fraction of a second after the Big Bang had to be fine-tuned to 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros, a number so vast it defies all human comprehension. Any tiny deviation from this perfect balance, by even 1 part in that astronomical number, would have been catastrophically amplified over cosmic time. A little too much density, and the universe would have collapsed back in on itself in a violent big crunch long before any stars could form. A little too little, and everything would have flown apart so quickly that not even atoms could have gathered together. We see neither of these fates. We see a universe that has persisted for billions of years, allowing for galaxies, planets, and life to emerge. How did our cosmos achieve this impossible, long-term balance on a cosmic tightrope? Once again, the same solution that resolved the other mysteries provides a breathtakingly elegant answer. A period of ultra-fast inflation would have acted like a master cosmic carpenter, taking any initial curvature and stretching space so enormously that it was smoothed out into the perfect flatness we observe. No fine-tuning required. The universe was not born perfectly balanced, it was stretched into shape, but this solution only pushes the mystery 1 step further back. What kind of physics could possibly command the very fabric of reality to execute such a perfect, reality-defining maneuver? This perfect flatness, however, is not the whole story. A sky of absolutely uniform temperature would have been a cosmic dead end, a featureless void with no potential for anything to ever form. The universe needed a blueprint for complexity, and it left one encoded in the faintest of imperfections. When we look at the cosmic microwave background with exquisitely sensitive instruments, we do not see a perfectly smooth canvas. We see a tapestry of incredibly subtle variations, tiny patches that are ever so slightly warmer or colder than the average. We are talking about differences of just 1 part in 100,000. It is the cosmic equivalent of a vast, calm ocean with ripples no higher than a single coin resting on its surface. Yet these minuscule ripples are the most important structures in the entire cosmos. They are the primordial seeds from which everything we know and love ultimately grew. Every galaxy, every star, every planet, and every one of us originated from these tiny wrinkles in the fabric of the early universe. Without them, gravity would have had nothing to grasp, no slightly denser regions to begin pulling matter together. The cosmos would have remained a formless, expanding cloud of gas forever. So where did these all-important seeds come from? Their origin lies in the most counterintuitive marriage of concepts imaginable, where the impossibly small directly engineered the impossibly large. The leading theory points to the same cosmic inflation that solved our other mysteries. In the frantic first moments, the universe was a seething sea of quantum fluctuations. On the tiniest of scales, particles and energy would wink in and out of existence, a constant froth of creation and annihilation dictated by quantum mechanics. Under normal circumstances, these fleeting fluctuations are utterly insignificant and vanish almost instantly. But during the hyper-fast stretching of inflation, something miraculous happened. The expansion of space was so rapid that it stretched these subatomic quantum ripples to astronomical sizes, freezing them into the very fabric of space-time. What was once a microscopic quantum jitter became a macroscopic density variation, a slight lump in the cosmic dough. This is a truly mind-bending concept. The same quantum physics that governs the behavior of atoms was amplified to sculpt the entire large-scale structure of the universe. The grand architecture of galaxy clusters and cosmic voids can be traced back directly to random quantum tremors in the first fleeting moments of time. It forces us to confront a staggering idea. Are we and everything we see simply the amplified echo of a quantum whisper? These quantum ripples were the raw material, but their ultimate fate was decided by a ghost. The detailed pattern of hot and cold spots in the cosmic microwave background is not random static. It is a cosmic ledger, a permanent record of a gravitational tug of war that began in the universe's infancy. The precise sizes and distributions of these spots tell a clear and startling story, one that points to the existence of a vast, invisible presence holding everything together, dark matter. To understand how, picture the early universe as a vast, hot soup of light and matter. In this dense plasma, ordinary matter, the stuff that makes up stars and planets, was constantly buffeted by the intense pressure of light. Gravity was trying to pull matter together to form the seeds of future galaxies, but radiation pressure was pushing it apart, creating a relentless struggle. Dark matter, however, is fundamentally different. It does not interact with light at all. It is completely transparent and invisible to electromagnetic forces. This means that while ordinary matter was being pushed around by the cosmic flood of radiation, dark matter was unaffected. It simply sat there, its own gravity pulling steadily, creating stable gravitational wells in the primordial darkness. The cosmic microwave background captures the moment this struggle ended, the instant the universe cooled enough for light to decouple from matter and travel freely across space. The pattern we see frozen in that light reveals which regions were under the gravitational influence of these stable dark matter wells. The sizes of the hot and cold spots are a direct measurement of the depth and scale of these invisible pits. The ledger shows that there had to be 5 times more of this invisible, gravitating substance than there was of the ordinary matter we can see. But the CMB tells us something even more specific about this ghostly material. It reveals that dark matter must be what scientists call cold. This does not mean it is chilly, but that it was moving relatively slowly in the early universe. If dark matter were hot, meaning it was zipping around at near light speed, its high velocity would have smoothed out the very small-scale ripples we see in the CMB. It would have erased the fine details of the cosmic ledger before they could be written. The fact that we see such a rich and detailed pattern of spots, especially on smaller scales, is definitive proof that dark matter was cold and sluggish, allowing its gravity to patiently sculpt the cosmos from the very beginning. This cold dark matter provided the stable gravitational scaffolding upon which the ordinary universe could later assemble itself. Every galaxy, every cluster, every filament in the cosmic web formed within the invisible architecture laid down by this mysterious substance. So, while we cannot see dark matter directly, the oldest light in the universe shows us its shadow, a ghostly signature imprinted forever on the sky. But the gravitational scaffolding of dark matter is not the only force shaping our cosmic fate. The very expansion of the universe, the rate at which space itself stretches, holds another secret, one that reveals a profound gap in our knowledge. This is the mystery of the cosmological constant, and it represents one of the most embarrassing failures in the entire history of theoretical physics. The problem begins with a simple yet revolutionary idea that empty space is not truly empty. According to quantum field theory, the vacuum of space is a seething, bubbling foam where virtual particles constantly pop into and out of existence. This activity should endow every cubic centimeter of nothingness with a certain energy, a pressure inherent to the vacuum itself. This vacuum energy is what scientists identify with dark energy, the force responsible for the accelerating expansion of the universe. The cosmic microwave background, combined with other observations, allows us to measure the actual strength of this dark energy. The value we get is incredibly small, but it is definitely not zero. It is just enough to cause the cosmic expansion to gradually speed up over billions of years. The mystery, the true embarrassment, lies in what our theories predict this number should be. When physicists calculate the theoretical value for the vacuum energy based on our best understanding of quantum mechanics, they arrive at a number that is astronomically larger. We are not talking about a difference of double or even 1,000 times. The predicted value is a number with 120 zeros after it, larger than the observed value. That is a discrepancy of 1 followed by 120 zeros. To grasp the sheer scale of this error, imagine predicting that a single grain of sand should weigh more than the entire observable universe. Our theoretical calculation is that grain of sand, and the observed reality is the entire cosmos. The difference is that vast, that incomprehensible. This is not a small oversight, it is a catastrophic failure. It means that our two most successful pillars of modern physics, quantum mechanics and general relativity, are fundamentally at odds when it comes to describing the energy of nothing. Something is terribly wrong. Either our understanding of the quantum vacuum is completely mistaken, or there is some miraculous, unknown cancellation mechanism that fine-tunes this enormous energy down to the infinitesimally tiny value we observe. Why is the energy of empty space so eerily quiet, so perfectly calibrated to allow for the existence of galaxies, stars, and life, when all our math screams that it should be a raging, universe-tearing inferno? This cosmological constant problem is a glaring signpost pointing toward a deeper layer of reality, a theory we have not yet discovered. This quiet vacuum energy is not the only thing behaving strangely. The very rate at which the cosmos is expanding has become the center of a modern crisis, a disagreement so stark it threatens to rewrite our cosmic rules. We call this the Hubble tension. At its heart is a simple number, the Hubble constant, which tells us how fast the universe is growing for every million light-years of space. For decades, astronomers have pursued this number with two powerful, independent methods. The first method uses the cosmic microwave background as a pristine time capsule. By meticulously analyzing the patterns in that ancient light, we can run the cosmic film backwards to understand the exact conditions of the infant universe, and then fast-forward it through our entire model of cosmic evolution to predict what the expansion rate should be today. This method gives us one very precise answer. The second method skips the ancient history and measures the expansion rate directly in our modern cosmic neighborhood. Astronomers use stars and exploding supernova as standard candles, objects with known intrinsic brightness, to gauge distances to nearby galaxies and clock their speeds. This local measurement gives us a different, equally precise number, and here is the crisis: these two numbers do not match. They disagree by a small but stubborn amount, a discrepancy that has only grown more significant as our measurements have become more and more accurate. This is not a minor statistical fluke, it is a persistent and growing crack in the foundation of modern cosmology. The early universe, as read from the CMB, suggests a slower expansion rate today than what we actually observe happening right now in our own cosmic backyard. So what could possibly explain this rift? One possibility is that there is a mundane, hidden error in one of our measurement techniques, an unknown systematic glitch fooling us. Yet after years of intense scrutiny, no such error has been found. the more thrilling possibility is that this tension is real and it is a signal of new physics. Perhaps our standard model of cosmology, which has been so successful, is missing a crucial ingredient, maybe an unknown type of exotic particle, a relic from the earliest times, is subtly altering the expansion history. Or perhaps dark energy itself is not a constant vacuum energy as we assume, but a dynamic force that has changed over time, a field that kicked in with a little extra push relatively recently in cosmic terms. This Hubble tension is a live wire in the world of astrophysics, an active debate happening in real time. It is a reminder that our map of the universe is not yet complete, and that the oldest light in the sky might be hiding one last revolutionary secret about the cosmos we call home. This disagreement over the expansion rate is not the only crack in our cosmic model. Even the pattern of the primordial ripples themselves holds a strange and persistent flaw, one that shows up on the very largest scales we can measure. This is the mystery of the anomalous quadrupole. When scientists decompose the map of the cosmic microwave background into its fundamental components, they look at different harmonic scales, much like listening to the individual notes that make up a complex chord of music. The quadrupole represents the very lowest note in this cosmic chord, the broadest, most sweeping fluctuations across the entire sky. According to our most trusted models of the early universe, this low note should ring with a certain expected power. But it does not. The observed quadrupole is far quieter than it has any right to be. The largest patterns in the universe are suspiciously muted, as if a cosmic hand has been placed over the speaker. At first, many hoped this was simply a statistical fluke, a random quiet patch in our particular corner of the cosmos. Yet as we have gathered more data, this lack of power has stubbornly refused to go away. It persists as a genuine anomaly, a whisper where we expect a shout. What could possibly suppress the universe's largest vibrations? One extraordinary possibility is that this is a clue to the overall shape, the global topology of all reality. Our standard assumption is that the universe is infinite and simply connected, like an endless flat plane. But what if it is not? What if space is finite but folded back on itself in a complex shape, like a three-dimensional donut? On such a grand topology, the very longest wavelengths, the ones that define the quadrupole, might not physically fit. They would be cut off, unable to oscillate, resulting in the exact lack of large-scale power we observe. It is as if we are living inside a cosmic concert hall whose dimensions are just a little too small to resonate with the deepest bass notes. This anomaly forces us to confront a humbling idea. We have been studying the cosmos in detail, but we may have completely misjudged its fundamental architecture. The quiet of the quadrupole could be the first faint echo of the universe's true, and perhaps surprisingly finite, shape. This unsettling quiet on the largest scales is not the only anomaly that defies our expectations. There is a deeper, more peculiar pattern hidden within the cosmic microwave background, one that seems to point a finger directly at us. When scientists look at the alignment of the very first few multipoles, the broadest waves in the cosmic chord, they find something truly bizarre. These fundamental patterns are not randomly oriented across the sky as the principle of isotropy demands. Instead, they appear to be loosely aligned with each other, and even more strangely, their geometry seems to be related to the plane of our own solar system. This unexpected coordination has been dramatically nicknamed the axis of evil, a label that reflects just how unsettling this finding is to our foundational cosmology. The entire cosmological principle rests on the idea that the universe has no preferred direction, no center, and no special place. It should look the same in every direction, a perfectly homogeneous and isotropic cosmos. The axis of evil suggests a faint, ghostly skeleton in the cosmic closet, a large-scale directionality that should not exist. It is as if the universe's background radiation has a subtle tilt, a whisper of a frame that just happens to line up with our local neighborhood. So, is this a cosmic coincidence, or is it a terrifying hint that we occupy a privileged position in the universe, a thought modern science has utterly rejected? The first and most conservative explanation is that this is not a feature of the universe at all, but a flaw in our perception. Perhaps it is an instrumental artifact, some unknown systematic error in how our satellites like Planck or WMAP have mapped the sky. Maybe residual light from our own galaxy, or even the movement of our solar system through space, is creating a faint, contaminating signal that imitates this alignment. Yet, after exhaustive checks and data cleaning, the peculiar alignment stubbornly persists. If it is not an error, then the implications are profound. One radical theory suggests this axis could be a fossil, an imprint from the era before cosmic inflation. Imagine that our universe did not begin in a state of perfect symmetry, but with some primordial structure or asymmetry. The subsequent inflationary expansion would have stretched that initial flaw to cosmic proportions, freezing its direction into the largest possible patterns we can see today. The axis of evil could be the faded scar of the universe's very first moments, a memory of a time before time settled into its current rules. Another, even more mind-bending possibility is that this alignment is a clue to something beyond our observable universe. If the cosmos is vastly larger than what we can see, the gravitational pull of an immense, unseen structure beyond our horizon could be subtly tugging on the fabric of our local space, leaving a directional warp in the ancient light. The axis of evil remains an unsolved and deeply controversial mystery. It challenges the very notion of a universe without a center, forcing us to wonder if the cosmos is truly indifferent to our place within it, or if the oldest light is trying to tell us that our location is, in some faint but measurable way, special after all. This unsettling sense of a special direction is not the only feature that makes our universe feel strangely personal. Tucked away in the southern galactic hemisphere lies one of the most baffling and persistent mysteries in the entire cosmic background, a place known simply as the cold spot. It is not just a minor statistical blip. This region of the sky is significantly colder than its surroundings, a colossal patch of chill that spans nearly 1 billion light-years across. Its sheer size and profound coldness defy easy explanation. When scientists first discovered it, the most logical assumption was that it was a vast cosmic void, an immense bubble of near emptiness in the cosmic web. The reasoning was elegant. As light travels across the universe, its photons climb in and out of the gravitational wells created by matter. When light enters a dense region, it gains energy, blue-shifting slightly. When it climbs out, it loses energy, red-shifting. But if a photon travels through a vast void, a region of below-average density, the effect is asymmetrical. It loses energy climbing into the void, but then has less gravity to fight against as it exits, so it does not regain all that energy. The net result is that light passing through a supervoid should appear slightly colder, a phenomenon known as the integrated Sachs-Wolf effect. The problem is, when astronomers went searching for the supervoid that could cause the cold spot, they found nothing large enough to account for it. There are voids in that direction, yes, but they are far too small and not nearly empty enough to produce such an extreme temperature drop. The observed cold is simply too great for the observed emptiness. So if it is not a void, what is it? The possibility that it is just a rare statistical fluctuation, a 1 in a million random cold patch in the cosmic tapestry, cannot be entirely ruled out. But the odds of such a massive anomaly appearing in our observable universe are incredibly low, making many scientists deeply skeptical. This has opened the door to far more exotic explanations, ideas that stretch the boundaries of physics itself. One of the most breathtaking hypotheses is that the cold spot is a cosmic bruise, a relic of a collision with another universe. This idea springs from the theory of eternal inflation and the multiverse. In this picture, our universe is just one bubble in a frothing, infinite meta-universe, where new bubble universes are constantly inflating into existence. Sometimes these bubbles can collide. If a neighboring universe bumped into ours during its own inflationary phase, the energy released at the boundary of that collision could have left a distinct imprint on our cosmic microwave background, a circular region of altered temperature. The cold spot has the right kind of profile to be the scar of such an unimaginable event. It would be the first empirical evidence that our cosmos is not alone, that we are part of a vaster, more complex multiverse. This single, mysterious cold patch in the ancient sky could be a window into the cosmos beyond our own, a permanent reminder that our Big Bang may have been just one birth among countless others. The debate over the cold spot remains wide open, a testament to the fact that even our most detailed map of the primordial universe still holds profound and unresolved secrets. This great cosmic quiet extends beyond the muted bass note of the quadrupole, revealing a deeper silence in the way the universe's hotspots relate to one another. When scientists study the cosmic microwave background, they do not just look at individual spots, they also analyze how these spots are connected. They measure the correlations, the statistical handshakes between a warm patch in one part of the sky and a cold patch in another. According to our most robust models of the primordial universe, temperature points separated by wide angles, more than 60 degrees on the sky, should show a certain level of coordinated behavior. They should be subtly linked like distant cousins who share a faint family resemblance. Yet, when we look at the actual data, that expected family resemblance vanishes. At these largest scales, the correlations are significantly weaker than they should be. The universe's primordial tapestry seems to be woven with threads that lose their connection across the vastest distances. It is as if you were looking at a pointillist painting and discovered that the dots on one side of the canvas have no artistic relationship whatsoever to the dots on the opposite side, defying the artist's unifying vision. So why would the universe's oldest light show such a profound lack of large-angle correlation? One compelling possibility is that this is another powerful clue to the cosmos's true shape and size. If the universe is not infinite but finite and multiply connected, like a hall of mirrors on a cosmic scale, its geometry would naturally impose a maximum possible distance over which any 2 points could be correlated. The patterns simply could not coordinate on scales larger than the universe itself. The missing correlations would then be a direct signature of the cosmos's finite extent, a fundamental cutoff written into the fabric of the ancient light. Another, even more profound explanation points us back to the very inception of time. This lack of correlation could be a fossil from the first fleeting moment of cosmic inflation. Our standard models often assume inflation started from a perfectly smooth, featureless state. But what if it did not? What if the inflationary expansion began from a chaotic, pre-existing quantum geometry where the concept of widely separated points being connected was not yet established? The rapid stretching of space may have then frozen this initial lack of large-scale connection into the cosmic microwave background, preserving a memory of the instant our universe truly began. This quiet, missing link between distant points is more than a statistical oddity. It is a potential window into the ultimate frontiers of reality, asking us whether we live in a cosmos with limits, and if the first moment of creation left its own unique, uncorrelated signature across the sky. This subtle preference for a cosmic handedness is one of the most peculiar clues hidden in the ancient light. When you look at your hands, you know they are mirror images, but they are not identical. You cannot fit a left-handed glove onto your right hand. This property is called parity, and for a long time, physicists believed the fundamental laws of the universe were perfectly symmetric under such a mirror reflection. A left-spinning particle and its right-spinning mirror twin should behave in exactly the same way. Yet, when scientists study the patterns in the cosmic microwave background, they find a faint but persistent whisper that this mirror symmetry might have been broken on the grandest of scales. The temperature fluctuations appear to show a slight preference for one type of spiral pattern over its mirror opposite. It is as if the universe in its first moments had a favorite hand for writing its initial conditions. This is the parity anomaly. If this signal is real and not just a statistical mirage, its implications are staggering. It would mean that the infant cosmos was not perfectly ambidextrous. Some fundamental process operating in that first searing instant imprinted a specific cosmic handedness across the entire observable universe. What kind of physics could possibly prefer left over right or right over left on such an unimaginable scale? The answer may lie in the realm of exotic fields and particles that we have not yet discovered. Certain theoretical models involve fields that couple directly to gravity and space-time itself in a way that naturally breaks parity. As the universe inflated, such a field could have stretched its own handed preference across the cosmos, etching it permanently into the gravitational waves and density ripples that later became the CMB. This would be a fossil of a force that operated only at energies far beyond anything we can recreate in our particle colliders. The parity anomaly is a ghostly signature, a potential message from an epoch where the very rules of left and right were being written into the fabric of reality. It challenges our assumption of a perfectly symmetrical beginning and suggests that the universe's first act may have chosen a side, setting the stage for everything that was to follow. This cosmic preference for a specific handedness is not the only way our universe seems to favor one side over another. As we map the sky in ever greater detail, another fundamental assumption begins to crumble, the idea that the cosmos is statistically the same in every direction. The data reveals a startling truth. One half of the cosmic microwave background is subtly but distinctly different from the other. This is the hemispherical power asymmetry. In the northern galactic hemisphere, the temperature fluctuations, those all-important primordial seeds, have a slightly higher amplitude. They are, on average, a bit more pronounced, a bit more vigorous. The southern hemisphere, by comparison, is marginally quieter, its fluctuations slightly more muted. It is as if the universe's volume knob was turned up just a little higher on one side of the cosmic concert hall. This is not a random smattering of hot and cold spots. It is a systematic, large-scale imbalance that seems to define a preferred axis in the sky, a new kind of cosmic equator dividing a more active north from a more passive south. Why would the primordial universe display such a fundamental lopsidedness? The principle of isotropy, the bedrock of modern cosmology, insists it should not. The universe is not supposed to have a more interesting half. The most straightforward explanation is that we are seeing a remnant of the inflationary epoch itself. Perhaps the field that drove inflation, the inflaton, was not perfectly uniform. It might have possessed a gentle gradient, a slight slope in its energy across space. As this field underwent its hyper-fast expansion, that initial slope would have been stretched across the entire observable universe. Regions that started with a slightly higher energy would have inflated a little differently, imprinting a slightly stronger power in the fluctuations that eventually became one half of our sky. This would mean the asymmetry is not a flaw in the universe, but a fossil of the inflaton field's own imperfect beginnings. Another, more radical possibility is that this asymmetry is not a relic of inflation, but a fundamental property of reality. We assume the cosmos is isotropic because it looks that way from our limited vantage point. But what if the universe is genuinely anisotropic on the very largest scales, with properties that genuinely vary with direction? Perhaps the density of dark energy or even the strength of gravity itself is not a constant throughout the cosmos, but changes gradually over distances so vast we can only perceive the beginning of the gradient. In this picture, our entire observable universe is just a small patch within a much grander and fundamentally lopsided cosmos. We are not at the center, but we are situated in a location where one side of our sky points toward a denser, more active part of the megaverse, while the other points toward a more dilute and quieter region. The hemispherical power asymmetry forces a profound question upon us. Is the universe's apparent uniformity just a local illusion, a quiet neighborhood in a cosmos that is, on the whole, wild and varied? The oldest light suggests our home may be perched on the slope of a much larger reality. This pristine signal from the dawn of time is not delivered to us on a clean channel. It is buried beneath a cacophony of cosmic static, a foreground of more recent emissions that we must carefully peel away to hear the universe's first whisper. Every object that has formed since the Big Bang, from the faintest, most distant galaxy to the immense clusters that bind them together, radiates its own light. This radiation overlaps with the cosmic microwave background, creating a layered map where the most ancient light is obscured by the brilliant glow of everything that came after. Isolating the true CMB is like trying to hear a single, quiet instrument in a roaring symphony. The process relies on a fundamental property of light, its frequency. Different astrophysical sources glow most brightly at different wavelengths. Distant galaxies shine in infrared, while hot gas in galaxy clusters emits X-rays. By mapping the sky across many different frequencies, from radio waves to far infrared, scientists can identify the unique spectral fingerprint of each contaminant. They build intricate models of these foregrounds, a cosmic noise profile, and then subtract them from the total signal. What remains, in theory, is the uncontaminated glow of the primordial universe. But this is where a deep and troubling uncertainty takes root. The subtraction is never perfect. Our models of galactic dust and distant radio sources are sophisticated, but they are still approximations. Tiny imperfections in the cleaning process could leave behind faint, residual signals that are not primordial at all, but merely the ghost of an imperfectly erased foreground. This risk casts a shadow of doubt over some of the most tantalizing anomalies we have encountered. Could the mysterious cold spot be explained not by a collision with another universe, but by an unseen cluster of distant, radio-quiet galaxies that our filters missed? Might the strange lack of large-scale correlation be an artifact of an oversubtraction in our galactic dust model? The terrifying possibility is that we are engaged in an archaeological dig, carefully brushing dust from a fossil, only to realize that some of the features we are most excited about might be chips from our own tools. The quest to see the first light is therefore a double mystery, a search for truth buried within the immense challenge of knowing what is truly signal and what is just the persistent noise of the evolving cosmos. This brilliant foreground static, however, is not merely noise to be discarded. One particular type of interference holds the key to mapping the invisible architecture of our modern universe. It is called the Sunyaev-Zeldovich effect, and it transforms the cosmic microwave background into a backlight for the largest structures in existence. As the ancient photons travel for billions of years to reach us, a small fraction pass through the immense clouds of hot gas that surround entire clusters of galaxies. This gas is so incredibly hot that it is ionized, meaning its electrons have been stripped from their atoms, creating a seething sea of free-moving particles. When a cold, primordial CMB photon enters this region, it has a chance of colliding with one of these high-energy electrons. In this scattering event, the photon steals a tiny bit of energy from the electron, like a small, lightweight ball gaining speed when it bounces off a much larger, fast-moving object. The photon is boosted to a slightly higher energy, leaving a distinct signature in its wake. This means that in the direction of a massive galaxy cluster, the cosmic microwave background does not appear perfectly pristine. Instead, it shows a specific distortion, a faint shadow or a slight brightening depending on the frequency we observe. For radio telescopes looking at the CMB's peak wavelengths, a cluster creates a small, dark patch against the glow. For instruments tuned to higher frequencies, the same cluster appears as a bright spot. This is not a temperature change in the universe itself, but a shadow play, a silhouette of modern structure cast upon the ancient screen of the Big Bang's afterglow. This effect is a phenomenally powerful tool for cosmologists, because the distortion strength depends almost entirely on the density of the hot electrons in the cluster, and not on how far away the cluster is. The Sunyaev-Zeldovich effect allows us to find galaxy clusters at staggering distances, all the way back to the earliest epochs of cluster formation. It is like having a searchlight that works just as well on objects near and far, enabling us to take a cosmic census and trace the growth of the largest gravitationally bound structures over the entire history of the universe. Yet this incredible tool also presents a formidable challenge. Each one of these distortions, each shadow cast by a cluster, is a contamination of the primordial signal we seek. To see the true, unaltered CMB, we must first find every single one of these imprints and subtract them with exquisite care. It is a delicate cosmic archaeology where we must first understand everything the universe built later, just to get a clear view of how it all began. But this shadow play of modern clusters is just one layer of interference. Beneath it lies a far more ancient and diffuse glow, a fossil from the era when the first stars ignited. This is the cosmic infrared background, the combined light of countless infant galaxies and the very first generation of stars, all blurred together into a faint, all-pervading fog. While the cosmic microwave background is a single snapshot from the universe's infancy, this infrared glow is like a long exposure photograph, capturing the entire, violent history of star formation that followed. It is the accumulated warmth of creation itself, shining across billions of years. This background presents a profound puzzle of its own. When we add up all the light from every galaxy we can see with our most powerful telescopes, the total falls short of the energy we detect in this diffuse infrared glow. There is a significant amount of missing starlight, the output of unseen primordial galaxies or incredibly dusty stellar nurseries that our current instruments cannot resolve individually. This tells us that our census of the early universe is still incomplete, that there are entire populations of faint, early objects whose combined radiance fills the cosmos with this unexplained warmth. This unresolved light directly interacts with our study of the CMB. The same hot, massive stars that produced this infrared glow also flooded the cosmos with ultraviolet radiation, which then began the epic process of reionization. That pivotal event when the first light broke apart the neutral hydrogen fog left its own distinct imprint on the polarization of the microwave background. So, by studying this cosmic infrared background, we are not just looking at starlight, we are tracing the very energy source that transformed the universe from a dark, simple place into the transparent, complex cosmos we see today. The mystery of its precise origin forces us to ask, what were those first galaxies truly like? How many of them remain hidden in the shadows, their collective glow a permanent testament to a dawn we are only beginning to perceive? Even this perfect blackbody glow might hide faint, ghostly scars. The cosmic microwave background spectrum is almost a textbook example of pure thermal radiation, a curve so smooth it seems to sing a single, perfect note. But what if that note has subtle, almost imperceptible harmonics? The hunt is on for these tiny spectral distortions, minute deviations from perfection that would reveal violent events in the cosmos' hidden childhood. Most of the universe's history was far too gentle to leave a mark on this robust background. But in the very first epochs, and again much later, certain cataclysmic processes could have injected enough energy to slightly warp this pristine spectrum, leaving behind permanent fingerprints. These imprints come in two primary forms, each telling a different story. The first is known as the Y distortion. This is a late-time effect created when the CMB photons pass through a vast sea of incredibly hot electrons. Imagine the ancient light wading through a scorching plasma, and with each collision, a photon gets a slight energy boost. This process does not create or destroy photons, but it does push them on average to slightly higher energies. It smears the perfect blackbody curve, leaving a telltale signature that we can associate with the formation of massive structures like galaxy clusters, or even from the collective heat of all the stars that have ever shone. The second type, the mu distortion, is far more ancient and profound. It originates from a much earlier era, before the universe was even 400,000 years old, when it was still so dense and hot that particles were constantly colliding and reshuffling energy. If a tremendous burst of energy was released during this period, say from the explosive decay of an unknown species of primordial particle or the evaporation of early black holes, that extra energy would have been quickly absorbed by the thick cosmic plasma. This would have increased the number of photons in the sea of radiation, effectively creating a chemical potential in the photon gas denoted by the Greek letter mu. It would be like adding extra water molecules to a perfectly still pond, not by making bigger waves, but by subtly raising the entire water level. Finding a mu distortion would be like discovering a fossil from the universe's first few 100,000 years, a period currently shrouded in near total darkness. It would be direct evidence of exotic physics in action, a sign that something beyond our standard model was at play in the cosmic dawn. Perhaps it could reveal the properties of dark matter itself, if certain types of it decayed and released their energy into the primordial soup. Or it might point to the existence of primordial black holes, evaporating in a brilliant flash that left a permanent scar on the light of creation. These spectral distortions are the faintest of whispers, requiring instruments of unbelievable sensitivity to detect. But if we can hear them, they will open a completely new window into the universe's most formative moments, allowing us to read chapters of cosmic history that have until now been entirely lost to time. Hidden within the gentle glow of the ancient light is a far more subtle message, a pattern of polarization that could reveal the universe's very first tremors. This is the hunt for B-mode polarization, one of the most important and difficult quests in all of modern science. To understand it, think of the cosmic microwave background not just as a tapestry of hot and cold, but as light that vibrates in specific directions. When the first atoms formed and set the primordial light free, that light was polarized, much like sunlight reflecting off the surface of a lake. This initial polarization, called E-mode, is a relatively simple pattern, like the rays of a star or the field around a magnet. It tells us about the density and motion of the ordinary matter in the infant cosmos. But theorists predict another, far more elusive pattern woven into this ancient light, the B-mode. This pattern has a distinct swirl, a curling signature like the water draining from a sink, and that specific swirl is the unique fingerprint of a gravitational wave. Not the gravitational waves we detect today from colliding black holes, but something infinitely more profound, primordial gravitational waves generated in the first frantic moments of the universe. These would be ripples in the very fabric of spacetime itself, created when the cosmos was a seething, energetic froth. The leading theory is that these waves were generated during the violent expansion of cosmic inflation, when the universe stretched faster than the speed of light. The energy scale of that inflation would have been so immense that it would have shaken the foundations of reality, sending tremors through spacetime that have been traveling for over 13 billion years. Detecting their signature in the B-mode polarization would be a direct line back to that epoch, a confirmation that inflation truly happened and a measurement of its incredible power. It would tell us what fueled the birth of our cosmos, but the implications run even deeper. These primordial gravitational waves are theorized to be of quantum origin, tiny fluctuations in the gravitational field that were stretched to cosmic size by inflation. Finding them would be the first ever evidence that gravity itself has a quantum nature, that the force which shapes the cosmos is at its heart a quantum force just like the others. This is the pivotal mystery of the B-mode signal. Its detection would be one of the greatest discoveries in the history of physics, confirming our grandest theories about the beginning of everything. Yet its continued absence, despite our most sensitive searches, is just as telling. It forces us to question whether inflation happened at all, or if it occurred at a much lower energy than we predict, pointing toward a different, perhaps even stranger, origin story for our universe. The search for this faint, swirling pattern in the oldest light is a race to answer the most fundamental questions we can ask. What set the universe in motion, and are the forces that govern it truly unified? The journey of this ancient light is not a straight path through empty space. Every photon from the cosmic dawn has traveled for over 13 billion years, and along its epic voyage, it has passed by trillions of suns, countless galaxies, and immense clouds of dark matter. Each of these objects, with its gravitational pull, acts like a lens, subtly bending the path of the light. This is the phenomenon of gravitational lensing, and it leaves a distinct smearing signature on the cosmic microwave background. The perfectly sharp primordial ripples we would expect to see are slightly blurred, as if we are looking at them through a cosmic window of frosted glass. This distortion is not a flaw in the data, it is a treasure map. By meticulously measuring how the CMB's patterns have been stretched and warped, scientists can trace the gravitational influence of all the matter that lies between us and the edge of the observable universe. This allows us to create a three-dimensional map of the cosmic web's dark matter skeleton with breathtaking precision. We are essentially using the oldest light in the universe as a backlight to illuminate the invisible architecture of everything that formed after it. Yet this powerful tool comes with a profound complication. The same lensing effect that reveals the dark cosmos also mixes the primordial signals we hold so dear. It scatters the light, transferring power from the large-scale patterns we understand well to smaller, more complex scales. This process can create subtle imitations of the signals we are desperately searching for, most notably the elusive B-mode polarization from primordial gravitational waves. A faint swirling pattern in the lensed CMB could be the echo of the universe's first tremors, or it could simply be the ghost of dark matter's gravitational hand, warping the simpler E-mode polarization into a false B-mode shape. Disentangling this cosmic illusion is one of the greatest challenges in modern cosmology. It forces us to understand the entire history of structure formation in perfect detail, just to be sure that the story we are reading in the ancient light is the original manuscript and not a copy edited by the gravity of everything that came after. This faint polarization in the ancient light carries a record of the universe's second great birth, the moment it was set ablaze. For hundreds of millions of years after the CMB was released, the cosmos was a dark, simple place, filled with a pervasive fog of neutral hydrogen gas. Then the first stars and galaxies ignited. Their intense ultraviolet radiation began to tear apart those hydrogen atoms, splitting them back into protons and electrons in an epic process called reionization. This was the final transition of the intergalactic medium from an opaque fog to the crystal-clear void we see between galaxies today. The cosmic microwave background holds the key to understanding this cosmic dawn, not through its temperature, but through the specific polarization imprinted as the last of those hydrogen atoms were being blasted apart. When a CMB photon scattered off a free electron during reionization, it gained a subtle directional preference, a specific polarization pattern known as E-modes. The strength of this signal tells us the total number of scatterings that occurred, a value scientists call the optical depth. It is a measure of how opaque the universe was to its own ancient light during this reionization era. The current measurement from the Planck satellite gives us a very precise number for this optical depth. This number, in turn, tells us that reionization must have been a relatively late and rapid process, concluding around when the universe was only a few 100 million years old. But here is where the mystery takes root. This timeline, written in the CMB's polarization, is now clashing with direct observations from our most powerful telescopes like the James Webb Space Telescope. We are now peering back at the very first galaxies, and what we are finding is deeply puzzling. There do not seem to be enough of these early, bright galaxies to produce the immense amount of ultraviolet radiation needed to reionize the entire cosmos so quickly. It is as if we have found a city completely illuminated, but when we count the power plants, we have only discovered a few small generators. The energy budget does not add up. So where did all the ionizing light come from? Perhaps the earliest galaxies were far more efficient at producing ultraviolet radiation than we thought, or maybe they were surrounded by fewer clouds of dust that could absorb their light before it escaped. Another, more exotic possibility is that the primary drivers of reionization were not these early galaxies at all, but something else entirely, like vast numbers of primordial black holes or even the violent deaths of the very first stars. The tension between the CMB story and the galaxy sensors forces a profound question. Are we missing an entire population of faint early galaxies, so dim that our telescopes cannot yet see them, but whose collective radiance was enough to clear the cosmic fog? Or is the optical depth trying to tell us that the universe's reawakening was driven by forces we have not yet even begun to imagine? The cosmic story etched in this ancient light reaches back even further than the formation of atoms, to a time when the entire universe was a nuclear furnace. In the first 3 minutes after the Big Bang, the cosmos was hot and dense enough to act as a primordial particle collider, fusing the first atomic nuclei in a process called Big Bang nucleosynthesis. During this fleeting epoch, protons and neutrons collided to form the cores of the lightest elements, primarily hydrogen and helium, with just traces of lithium and deuterium. The precise recipe for this elemental soup was determined by a few key factors: the density of ordinary matter, the expansion rate of the universe, and the number of types of lightweight particles like neutrinos flooding the cosmos. For decades, our best estimates of that primordial helium abundance came from studying the oldest, most metal-poor stars and gas clouds in our galaxy. But these are indirect measurements looking at material that has been processed and altered over billions of years. The cosmic microwave background offers a far more pristine time capsule. By analyzing the subtle details of the CMB's temperature and polarization fluctuations, we can essentially weigh the total amount of ordinary matter present in the early universe. Since the outcome of Big Bang nucleosynthesis is exquisitely sensitive to that matter density, this CMB measurement allows us to predict, with remarkable precision, exactly how much primordial helium should have been forged in that first cosmic fire. And here, a subtle but persistent mystery emerges. The amount of helium inferred from the CMB is just a little bit higher than what the standard model of particle physics predicts. It is a small discrepancy, only a % or 2, but in the world of precision cosmology, even a tiny tension can signal a crack in our understanding. This surplus of primordial helium suggests that the conditions in the first 3 minutes were slightly different than we thought. One compelling explanation is that there were more types of lightweight particles contributing to the energy density of the young cosmos. The standard model of particle physics includes 3 known types or flavors of neutrinos. But what if there was a fourth, a sterile neutrino that we have not yet detected? This extra particle would not interact through the weak force like ordinary neutrinos, but its gravitational presence would have made the universe expand just a fraction faster during those critical first minutes. A faster expansion would have shut down the nuclear fusion process a little sooner, leaving more free neutrons available to be locked up into helium nuclei. The result, a universe with a slightly higher helium abundance than expected, exactly as the CMB seems to suggest. Another, even more radical possibility is that the fundamental constants of nature themselves were not so constant in the universe's first moments. What if the strength of the weak nuclear force, which governs how quickly neutrons convert into protons, was subtly different back then? A minor variation in this force would have dramatically altered the proton-to-neutron ratio available for fusion, directly impacting the final helium yield. The faint helium signature in the CMB is therefore a potential window into physics operating at energies we can never hope to recreate in a laboratory. It asks a profound question: were the rules of the game set in stone from the very first instant, or did the universe begin with its dials tuned to slightly different values, leaving behind a trace of its initial strangeness in the abundance of the very first elements? This faint trace of primordial helium is not the only elemental secret the ancient light can reveal. It also acts as a cosmic scale, one sensitive enough to weigh the lightest, most ghostly particles in existence. The cosmic microwave background, when combined with the large-scale structure of the modern universe, places a remarkably tight constraint on the total mass of neutrinos. These elusive particles are so lightweight and interact so weakly that for decades, physicists assumed they were completely massless, zipping through the cosmos at the speed of light. We now know they must have some mass, but the exact amount has remained one of particle physics' most stubborn mysteries. The CMB provides the answer not by seeing neutrinos directly, but by feeling their gravitational shadow. In the early universe, neutrinos were moving at nearly light speed. This high velocity gave them a unique property. They could stream freely out of dense regions, washing out the very small-scale clumping of matter. The precise pattern of galaxy clusters and cosmic voids we see today, and the detailed texture of the CMB itself, are exquisitely sensitive to this smoothing effect. The data tells a clear and startling story. The combined mass of all three neutrino types must be vanishingly small, less than a tenth of a single electron volt. To grasp how inconceivably tiny this is, consider that an electron, itself a lightweight particle, is over 500,000 times heavier. The universe itself is telling us that neutrinos are almost but not quite nothing. This creates a profound puzzle. While this upper limit from cosmology is a triumph of measurement, it sits in an uncomfortable space. Some theories beyond the standard model of particle physics predicted that neutrinos could be significantly heavier. The fact that they are so impossibly light begs the question, why? What mechanism or symmetry in nature forces these fundamental particles to be so close to weightlessness when all their other family members, like electrons and quarks, have substantial mass? Pinning down the exact mass would do more than just solve a particle physics puzzle. It would open a window into the highest energy scales imaginable. The tiny neutrino mass is thought to be a clue to grand unified theories, potential frameworks that weave all the fundamental forces into a single tapestry. Each decimal place we shave off the neutrino's mass rule out entire families of these ambitious theories, guiding us toward the ultimate laws of nature. The oldest light in the sky is therefore weighing in on the smallest of scales, using the grand architecture of the cosmos to illuminate the secrets of the quantum world. The primordial ripples have their own unique fingerprint, a subtle hierarchy of size and strength that tells us exactly how the universe was stretched into being. This fingerprint is known as the scalar spectral index. In essence, it is a single number that measures how the power of those initial quantum fluctuations depends on their physical scale. Think of the early universe as a vast drumhead being struck by quantum mechanics. A perfectly scale invariant spectrum would mean that every single beat, from the tiniest tap to the loudest bang, carried exactly the same energy. The drum would have no preferred rhythm. If that were the case, the scalar spectral index would be exactly 1, but the universe we observe is not that simple. Our most precise measurements from the cosmic microwave background reveal a value that is slightly, but definitively, less than 1. This means that the largest scales, the deepest bass notes in the cosmic chord, are slightly stronger than the smaller, higher-pitched notes. The infant cosmos had a preference for the grand over the minute. This tiny deviation from perfection, this faint red tilt in the spectrum, is one of the most profound clues we have about the inflationary epoch. It acts as a ruthless judge for the countless theoretical models of inflation that physicists have devised. Any model that predicts a spectral index of 1 or greater is immediately ruled out by the data. The observed value of slightly less than 1 strongly favors a specific class of inflationary scenarios, those where the energy field driving the expansion, the inflaton, was slowly rolling down a gentle slope of its potential energy. This slow roll is crucial. It produces just the right kind of slight imbalance in the fluctuation spectrum that we see imprinted across the sky. Yet for all its power to discriminate between theories, the scalar spectral index presents a deep mystery of its own. Why does it have the precise value that it does? Why is it 0.96 or so, and not 0.98 or 0.94? This number is not a random accident. It is a direct reflection of the specific shape of the inflaton field's potential energy landscape. The exact slope and curvature of that hill in the first fraction of a second determined this number for all time. But we have no fundamental theory that tells us why that particular hill was the one our universe rolled down. Out of an infinite number of possible inflationary landscapes, why did nature choose this one? The answer to that question would unlock the true identity of the inflaton field itself, revealing what kind of physics actually powered the birth of our cosmos. For now, this single, precise number remains a silent sentinel, a code from the beginning of time that we can read perfectly but cannot yet fully decipher. Even the universe's preference for grand scales might not be a fixed rule. The subtle red tilt of the primordial fluctuations, the scalar spectral index, appears to be a single, constant number across the sky. But what if this number itself is not a constant? What if it changes or runs as we look at different scales? This is the tantalizing mystery of the running of the spectral index. It suggests that the very character of the initial quantum jitters may have been evolving during the frantic inflationary expansion. Imagine the inflaton field not as a ball rolling smoothly down a single, gentle hill, but as one navigating a more complex, textured landscape. A slight change in the steepness or the curvature of that hill during the roll would have imprinted a change in the fluctuation spectrum. The largest scales, which exited the horizon first, would carry one signature, while the smaller scales, which exited later, would carry a slightly different one. A detection of this running would be like finding a fossilized video of the inflationary process itself, rather than just a single snapshot. It would reveal the dynamic nature of the field that birthed our cosmos, providing a direct measurement of the intricate shape of its potential energy. Current data from the cosmic microwave background, however, places this idea in a state of profound suspense. The measurements are so precise that they tightly constrain any possible running, effectively ruling out large, dramatic changes. The spectral index appears remarkably constant, yet the door is not completely closed. The data still allows for a very small, subtle level of running, a whisper of a change that is too faint for our current instruments to confirm or deny. This leaves us with a critical, open question. Is the running exactly zero, indicating an inflaton field of breathtaking simplicity, or is there a tiny, non-zero value waiting to be discovered, pointing toward a more complex and rich inflationary physics? The answer holds the key to understanding not just that inflation happened, but precisely how it unfolded in that first fleeting moment of creation. This single number, the tensor to scalar ratio, holds the key to the universe's violent birth. Known simply as R, it measures the relative power between two fundamental types of primordial ripples. On one hand, you have the scalar fluctuations, the density waves that seeded all the galaxies and stars. On the other, you have the tensor fluctuations, the primordial gravitational waves that shook the fabric of spacetime itself. The ratio R tells us which of these two choruses was louder in the first instant. Was the newborn cosmos dominated by the gentle hills and valleys of matter, or was it ringing with the violent tremors of gravity? The answer to this question reveals the energy scale of inflation, the sheer, raw power that drove the universe's exponential growth. It is a direct probe into the physics operating at nearly 10 to the power of 16 gigaelectronvolts, an energy a trillion times greater than what our most powerful particle colliders can ever hope to achieve. Yet for all its importance, this crucial number remains stubbornly elusive. Our most sensitive experiments have so far found no definitive trace of these primordial gravitational waves, meaning the value of R must be incredibly small. This profound silence is a major crisis for many of the simplest and most elegant models of inflation. Grand, powerful inflationary theories predicted a loud, clear signal, a gravitational wave background that should have been within our reach to detect. The fact that we hear nothing suggests that inflation, if it happened at all, was a much quieter, gentler process than we had anticipated. It forces us to ask a humbling question. Were we completely wrong about the ferocity of our own universe's creation? The ongoing hunt for R is not just a technical challenge, it is a philosophical one, forcing us to reconsider the very nature of the cosmic dawn and what it truly means to emerge from nothing. This perfect cosmic fingerprint, however, might hide tiny, telling imperfections in its swirls. For all its apparent randomness, the pattern of hot and cold spots in the cosmic microwave background is assumed to follow a specific statistical rule known as a Gaussian distribution. Imagine you are rolling a pair of dice over and over again. Most of the time you will roll a 7. Rolling a 2 or a 12 is far less likely, but it is possible, and the odds of these extreme outcomes are precisely predictable. This bell curve of probability is what we mean by Gaussian. In the cosmic context, it means that the size and distribution of the warm and cold patches should be completely random. A particularly hot spot should be just as likely as a particularly cold one, and they should have no secret correlations or special shapes linking them together. This assumption of perfect randomness is a direct prediction of the simplest models of inflation, where a single, smooth energy field stretched space and froze in the quantum jitters. But what if the dice were subtly loaded? The intense search is on for any deviation from this Gaussian ideal, a signature known as non-Gaussianity. This would appear as strange, unexpected correlations between different spots in the sky. Perhaps 3 specific cold spots would form a distinct, connected triangle much more often than pure chance would allow. Or maybe the hottest spots would have a distinctly squashed or stretched shape, a statistical preference that pure randomness cannot explain. Finding even a hint of such a pattern would be a monumental discovery, as it would shatter the simplest story of cosmic birth. A detection of non-Gaussianity would be a clear sign that inflation was not driven by a single, serene field rolling down a gentle hill. Instead, it would point to a far more dramatic and complex genesis. Picture multiple energy fields interacting violently, like balls bouncing and colliding in a pinball machine during that first explosive moment. Or imagine cosmic strings, defects in spacetime itself, forming and stretching during inflation, leaving sharp, non-random scars on the primordial canvas. These more intricate physics would naturally create those subtle correlations, those loaded dice that we search for. The profound silence so far, the fact that the fluctuations appear exquisitely Gaussian, is itself a powerful statement. It tells us that whatever gave birth to our universe, it was an incredibly smooth and simple process on the grandest of scales. Yet the hunt continues because finding even the faintest whisper of non-Gaussianity would open a window into a chaotic, multi-faceted dawn, a first instant far richer and more turbulent than our most elegant theories have dared to suggest. The perfect randomness we assume may be a grand illusion hiding the true architecture of all reality. This brings us to a mystery that questions the very extent of existence, the topology of the universe. We naturally imagine the cosmos as an infinite, featureless void, stretching forever in all directions. But what if it is not? What if the universe is finite but folded back on itself in a complex, multi-connected shape, like a three-dimensional donut known as a three-torus? In such a cosmos, if you could travel in a straight line for long enough, you would not journey forever into nothingness. Instead, you would eventually return to your starting point from the opposite direction, like an ant walking on the surface of a sphere. This mind-bending possibility is not just a mathematical curiosity. It leaves a direct, testable fingerprint on the cosmic microwave background. Because space would wrap around on itself, light would have multiple paths to reach us from a single, primordial source. Imagine the CMB as a vast, glowing wallpaper pattern covering the walls of a room shaped like a hall of mirrors. In a simply connected, infinite universe, every patch of that wallpaper is unique. But in a finite, multiply-connected one, you would see the same repeated patterns, the same set of hot and cold spots, appearing in multiple, correlated locations on the sky. Scientists search for these ghostly correlations, for matched circles of temperature that should not exist if space were truly infinite and flat. They are looking for the telltale seams in the fabric of reality, the places where the universe stitches back into itself. Finding such a signature would be one of the most profound discoveries in human history. It would mean our entire cosmos is a finite entity with a specific, albeit unimaginably vast, shape. The ongoing search for these cosmic echoes is a silent, mathematical hunt through the oldest light, a quest to determine if we live in a boundless expanse or within a structured, perhaps even knowable, cosmic home. This cosmic hall of mirrors might be just one room in an infinite mansion. The same physics that gave us our smooth, flat universe may have also created an endless multiverse, a reality where our Big Bang was not a unique beginning but a common event. The theory of eternal inflation suggests that the vacuum of space possesses a strange, high-energy state that drives exponential expansion. In this picture, our entire observable universe is just one bubble that randomly formed when the inflattened field in our region decayed, releasing its pent-up energy to create the hot soup of the Big Bang. But elsewhere, in the eternally inflating background, this process never stops. New bubble universes are constantly budding off, each with its own random set of physical laws and constants. Our cosmos, with its specific particle masses and force strengths, might be just one accidental outcome in a frothing sea of infinite possibilities. The cosmic microwave background could be our local bubble's birth certificate. The specific pattern of fluctuations we see, the precise value of the spectral index, and even the strange anomalies like the cold spot, might not be fundamental truths of all reality. They could simply be the initial conditions that were frozen into our particular pocket of the multiverse when our bubble nucleated and stopped inflating. This idea transforms the CMB from a map of the entire cosmos into a window looking out from our own cosmic neighborhood. The mysteries we have been grappling with take on a completely new meaning. Why is the cosmological constant so unnaturally small? In the multiverse picture, it is not fine-tuned. Across the infinite ensemble of universes, every possible value occurs. We simply find ourselves in one of the rare bubbles where the vacuum energy is quiet enough to allow for galaxies and life to form. The same logic could apply to the strength of gravity or the mass of the electron. The fundamental numbers we measure are not laws, they are local bylaws, the environmental conditions of our cosmic habitat. The search for a single, elegant theory of everything might be misguided if our universe is just one random draw from a cosmic lottery. The ancient light we study so carefully may be telling us the ultimate secret, that we are living in a single page of an infinite library, a library whose full scope we may never truly comprehend. These profound clues from the CMB lead us back to the ultimate precipice, the edge of time itself. The cosmic microwave background is our earliest photograph of the universe, a snapshot taken when it was a mere 400,000 years old. But this picture, for all its detail, is also a wall. It marks the limit of our vision, the moment the cosmos became transparent. Before that wall lies the realm of the initial singularity, the hypothetical point of infinite density and temperature from which the Big Bang is said to have sprung. The CMB is our most powerful tool to probe this ultimate mystery, yet its very nature may be hiding the answer. The profound smoothness and flatness we observe are the direct results of cosmic inflation, a period of hyper-fast stretching that ironed out the cosmos. This same process, which solved so many puzzles, may have acted as the ultimate cosmic eraser. Any information about what, if anything, came before the singularity, any trace of a prior state of existence, would have been stretched and smoothed into oblivion by the violent expansion. It is as if the universe took its own birth certificate and ran it through a shredder, then scattered the fragments across an infinity of space. The immaculate canvas of the CMB is beautiful, but it is also silent on the most fundamental question of all. Was the singularity a true beginning, a moment of pure creation from nothing? Or was it a transition, a bounce from a previous cosmic cycle that contracted down to a single point before rebounding? The CMB's serene face gives no indication. Its smoothness is the very reason we cannot see past it to the singularity. We are left staring at a blank wall, knowing that the most important event in history occurred just on the other side, its secrets permanently veiled by the very process that made our universe habitable. The initial singularity remains the final, untouchable mystery, a silent genesis whose true nature the oldest light refuses to reveal. The serene face of the cosmic microwave background might be hiding the most violent secret of all, a record of the moment gravity itself was born. We have journeyed through the universe's first atoms, its first stars, and its first particles, but now we approach the final frontier, the quest to see gravity's quantum heart. The smooth, classical canvas we observe is the end result of a process that began in a realm of pure quantum chaos, where spacetime itself was a seething, probabilistic foam. The grand mystery of quantum gravity is that we have no theory to describe this epoch. Einstein's general relativity, which governs the cosmos on large scales, and quantum mechanics, which rules the tiny world of particles, are fundamentally incompatible. One describes space and time as a smooth, continuous fabric, while the other insists that at the very smallest scales, this fabric must be granular, discrete, and fuzzy. For decades, the search for a theory that unites them, like string theory or loop quantum gravity, has been a purely mathematical pursuit with no experimental data to guide the way. But the cosmic microwave background offers a stunning possibility. It is the only witness to an era when the universe was so small that quantum gravitational effects should have been dominant. The process of cosmic inflation is the crucial link. Think of inflation as the cosmic amplifier. It took the infinitesimal quantum fluctuations of the pre-inflationary universe and stretched them to astronomical sizes. Most of these fluctuations were in the matter and energy fields, giving us the scalar seeds for galaxies. But what about the fluctuations in the fabric of spacetime itself? These primordial gravitational waves are the tensor signal we search for, and they are a direct probe of the energy scale of inflation. But if the theories are correct, the transition from the quantum gravity regime to the classical, smooth universe we see today could have left its own unique signature. This would be a subtle deviation in the pattern of the gravitational waves, a faint echo of the granularity of spacetime. Imagine the infant universe as a pond whose surface is not perfectly still, but is made of a billion tiny, vibrating droplets. As the pond freezes into a smooth sheet of ice, the pattern of the freezing might preserve a memory of that underlying granular texture. In the same way, the act of inflation freezing the quantum fluctuations into classical, permanent ripples might have imprinted a statistical tell, a specific kind of non-Gaussianity or a particular twist in the polarization of the gravitational wave background that betrays the quantum nature of gravity at its source. Detecting such an imprint would be the discovery of the millennium. It would not just confirm a specific theory of quantum gravity, it would validate the entire concept. For the first time, we would have experimental evidence of physics at the Planck scale, a realm so tiny that a single atom is as vast compared to it as our entire solar system is to that atom. The hunt for these quantum gravity imprints is the ultimate treasure hunt, a search for a whisper from the moment time and space first crystallized into the reality we know. It turns the cosmic microwave background from a map of our cosmic origins into a potential portal, a window into the fundamental architecture of existence itself. One possible key to the Hubble tension could be a ghost that faded away. This is the radical proposal of early dark energy, a transient and exotic form of energy that may have surged through the cosmos for a brief moment in its youth, only to vanish without a trace. Imagine a temporary assistant that gave the universe an extra, gentle shove during its first 100,000 years, slightly altering the rhythm of its expansion. This fleeting presence would have left a distinct fingerprint on the cosmic microwave background, a subtle shift in the very sound waves that rippled through the primordial plasma. These are the acoustic peaks, the frozen harmonics of the universe's first cry. The precise spacing and height of these peaks are a cosmic tuning fork, calibrated by the ingredients of the early universe. If a form of early dark energy was present, it would have added an extra component to the cosmic energy density, changing the way gravity and radiation pressure competed. This would have subtly altered the push and pull on those primordial sound waves, shifting the positions of the peaks in a way that our telescopes can, in theory, measure. It would be like hearing a familiar symphony played in a slightly larger concert hall, the same notes echoing with a different resonance. Scientists are now scouring the CMB data with forensic precision, looking for this specific spectral shift. A confirmed detection would be a revolution, revealing that dark energy is not a constant, silent force, but a dynamic entity that can come and go, shaping the cosmos in fleeting, powerful episodes. It would mean the vacuum of space has a memory and a history, one where its own energy could flare up and then fade, leaving behind only a single, persistent disagreement in our measurements as the final clue to its existence. But this cosmic symphony of light and gravity may be orchestrated by another, invisible force. The universe could be threaded with vast, primordial magnetic fields, stretching across billions of light years from its very first moments. These are not the familiar magnetic fields of stars or galaxies, which are generated by moving plasma. These would be cosmic fossils woven into the fabric of space itself during its birth pangs. Their existence would solve several profound puzzles at once, yet their origin remains one of cosmology's most tantalizing unknowns. How could we possibly detect such a ghostly presence? The answer lies in the subtle dance of the ancient light. As the photons of the cosmic microwave background travel across the cosmos, a large-scale magnetic field would gently twist their polarization. It would impart a specific swirling pattern, a signature known as Faraday rotation. This effect would subtly mix the E-mode and B-mode polarizations we discussed earlier, leaving a distinct, non-random fingerprint across the sky. Scientists are now hunting for this precise twist in the CMB's polarized light, a signal that would be the definitive proof that the universe was magnetized from the very beginning. The implications of such a discovery would be staggering. These primordial fields could be the very reason we see some of the large-scale anomalies that defy our standard models. That strange hemispherical power asymmetry, where one half of the universe seems more vigorous than the other, could be explained by a large-scale gradient in the strength of this background magnetism. The mysterious lack of correlation on the largest angles could also be a consequence of these fields altering the propagation of the primordial sound waves. But their existence raises an even deeper question. What physical process in the first instance of the Big Bang could have generated such immense, organized magnetic fields? Our current understanding of physics provides no easy answer. It would require a revolution pointing to new types of particles or forces active in that searing first second, a physics that left its permanent magnetic signature on everything. Finding these fields would mean our universe is not just expanding and filled with dark matter, but is also fundamentally magnetic, a cosmos humming with a hidden force that has guided its evolution from the very first moment. The universe's smooth tapestry might be hiding tears in the fabric of space-time itself. These hypothetical flaws are known as cosmic strings, and they are among the most dramatic relics our telescopes have never seen. Born from the intense energy of the universe's first moments, they are thought to be infinitesimally thin, yet unimaginably dense filaments, thinner than a proton but with the mass of a mountain range packed into every inch. They would be like cracks frozen in the cosmic ice as the universe cooled and underwent profound phase transitions, similar to the fissures that form in water as it freezes. If they exist, these cosmic strings would stretch across the cosmos, forming a network of immense gravitational landmarks. Their presence would warp the space around them so severely that they would act as natural gravitational lenses, bending the light from distant galaxies into double images. But their most distinctive signature would be carved directly into the cosmic microwave background. As a cosmic string moves through space, it creates a wake. The immense gravity of the string pulls matter and radiation toward it, but because it is a one-dimensional defect, the effect is incredibly sharp. It would not create a broad, gentle hill of temperature like a galaxy cluster, but a razor-thin, line-like discontinuity in the CMB temperature map. Imagine looking at a perfectly smooth, painted wall and seeing a single, perfectly straight crack where the color on one side is abruptly different from the other. That is what a cosmic string would do to the ancient light. On one side of the string, space-time is slightly compressed, making the CMB photons there appear a tiny bit warmer. On the other side, space-time is stretched, making the photons appear cooler. This creates a pair of sharp, linear cold and hot edges right next to each other in the sky, a step-like discontinuity that is completely unique. It is a signature that is both simple and dramatic, a scar that would be impossible to ignore. Yet, despite decades of searching through the CMB data with algorithms designed to find such straight-line features, we have found nothing. No convincing, sharp crack has been discovered in the primordial glow. This profound absence is itself a powerful clue. It tells us that the early universe's transition to its current state was likely very smooth, without the violent snapping and cracking that would have left these cosmic scars behind. The continuing silence of the strings forces us to ask a deeper question. Did the universe cool with such perfect grace that it avoided creating any permanent defects, or are these strings simply too faint, too cosmic for our current eyes to see? Their elusive nature keeps this mystery alive, a ghostly possibility that the oldest light might still be hiding the sharpest of all its secrets. The very laws of physics might not be as constant as we believe. We take for granted that numbers like the fine structure constant, which governs the strength of electromagnetism, are fixed pillars of reality. They dictate how atoms form, how light interacts with matter, and crucially, how the first atoms came together in the early universe. But what if these pillars could sway? The cosmic microwave background offers a way to test this radical idea, because it is a direct fossil of that first atomic formation. The moment of recombination, when electrons and protons combine to form neutral hydrogen, was a precise dance dictated by the fine structure constant. If this constant had been even slightly stronger in the past, electrons would have been bound more tightly to atomic nuclei. This would have made atoms form earlier when the universe was hotter and denser. An earlier recombination would mean the surface of last scattering, the source of the CMB, was a little bit closer to the Big Bang. The travel time for those first photons would have been different, subtly changing the apparent size of the horizon at that moment. This altered horizon size would then be frozen into the cosmic microwave background as a measurable shift in the scale of the acoustic peaks, the characteristic pattern of hot and cold spots. It would be like hearing a familiar song played on a piano that was tuned slightly sharp. The melody is the same, but the pitch is unmistakably off. Scientists are now scouring the CMB data for exactly this kind of spectral shift, hunting for a whisper that the rules of the game were once written with a different pen. A detection would be a scientific earthquake, forcing us to rewrite our understanding of reality's most basic foundations. Why would the constants of nature change? Some theories suggest they are not fundamental at all, but are the outcome of extra, hidden dimensions of space that have slowly stabilized over cosmic time. Others propose they are linked to dynamic fields that have gradually evolved since the beginning. If the constants can vary, then the universe is not a static arena governed by eternal laws, but a participant in its own story, its very physical fabric slowly evolving. The ancient light is not just a snapshot of a moment, but a potential time lapse of the laws of physics themselves, a record of a time when the universe operated by a slightly different set of rules. Our galaxy's own dust clouds are whispering a lie that sounds like the truth. This is not the simple dust you wipe from a shelf, but a complex mist of interstellar grains aligned by the Milky Way's magnetic field. When starlight hits these tiny, needle-like particles, they don't just glow, they glow with a specific, twisted polarization. And this polarized dust emission creates a signal that is hauntingly similar to the one we are desperately searching for, the primordial B-mode polarization from gravitational waves. The dust's own swirling pattern can perfectly mimic the signature of the universe's birth pangs. This creates a perilous crossroads in cosmology. The risk is not just that we might overlook a real signal, but that we might confidently announce a discovery that is nothing more than a local illusion, a trick of the galactic foreground. The challenge lies in the dust's bewildering complexity. Its properties are not uniform, changing dramatically from one region of the sky to another. Some clouds are warmer, some colder, some more densely packed, and all are threaded by a magnetic field whose detailed structure we barely understand. To peel this dust away and see the pristine CMB beneath, we must create a perfect model of its behavior across every frequency. But our models are still approximations, built on incomplete maps and assumptions. If we misjudge the dust's intensity by even a small amount, or misread the character of its polarization, we could be left with a residual signal that looks convincingly primordial but is entirely manufactured by our own imperfect cleaning process. It is the ultimate cosmic archaeological problem where the most sought-after treasure could be a masterfully crafted fake, buried not by time but by our own galactic backyard. The entire hunt for the universe's first gravitational waves hangs in the balance, dependent on our ability to fully understand the subtle, swirling language of galactic dust. This delicate dance with galactic dust is just one part of a much larger struggle. Every single whisper we extract from the cosmic microwave background is filtered through the immense and imperfect machinery of our own creation. The hunt for these primordial truths is a constant battle against systematic errors, tiny flaws in our experiments and methods that can conjure phantoms or erase real signals altogether. These are not simple mistakes, but subtle, persistent biases built into the very act of observation. Consider the telescope itself, a masterpiece of engineering that is nonetheless imperfect. Its main mirror or lens might have a minuscule asymmetric distortion in its shape, an imperfection smaller than the width of a human hair. This tiny flaw, known as a beam asymmetry, means the instrument does not see a perfect circle in the sky, but a slightly elongated or squashed oval. As this distorted beam scans across the heavens, it smears the pristine cosmic signal, subtly altering the shapes of the hot and cold spots. A perfectly round primordial ripple could be stretched into an oval, mimicking the specific polarized signature of gravitational waves or creating a false axis of alignment where none exists. Untangling this instrumental fingerprint from the true cosmic one requires a level of self-knowledge so precise it borders on the philosophical. We must know our own tools better than we know the sky. Then there is the challenge of calibration. To translate the raw voltage readings from our detectors into a precise temperature map of the sky, we need an absolute reference, a cosmic ruler for temperature. Scientists often use celestial objects with known, stable emissions, or even the dipole pattern caused by our own motion through space as these fundamental standards. But if our understanding of that reference is off by even a fraction of a percent, that tiny error propagates through the entire dataset. It can make the entire sky seem slightly warmer or cooler than it truly is, or more dangerously, it can alter the perceived strength of the fluctuations. A 1% calibration error might not sound like much, but when we are measuring differences of 1 part in 100,000, it is enough to completely distort our view of the primordial universe, potentially hiding a faint gravitational wave signal or exaggerating the significance of a strange anomaly. The data's journey from raw signal to cosmological revelation is a gauntlet of choices and assumptions. The algorithms that process the terabytes of satellite data must make decisions about how to filter out noise, how to combine observations from different frequencies, and how to stitch together maps of the entire sky. Each choice is a potential fork in the road. An overly aggressive filter designed to remove galactic dust might also erase a genuine, large-scale feature in the CMB, like the muted quadrupole. A particular method for estimating the noise could inadvertently create patterns that look like the swirling B modes we so desperately seek. The terrifying truth is that the line between a profound discovery and a sophisticated instrumental artifact is vanishingly thin. We are not just observing the universe, we are in a constant dialogue with the limits of our own perception, forever wondering if the ghost we see is a message from the dawn of time or merely the shadow of our own magnificent, flawed machines. This profound limitation strikes at the very heart of cosmology. We have constructed our grand theories of the universe from a single data point, one solitary sky. This is the problem of cosmic variance, a fundamental statistical uncertainty that arises because we can only observe one realization of the primordial random process. When we roll the cosmic dice, we only get to see the result once. This places an absolute ceiling on the precision of our knowledge, especially for the largest scales in the universe. Think of it like trying to understand the average height of all humans by only ever measuring one single person. You might get lucky and pick someone of average height, or you might pick a basketball player or someone very short. From that one measurement, you have no way of knowing how representative your sample is of the entire population. In cosmology, the entire observable universe is our one and only sample. The largest structures we can see, like the broadest waves in the cosmic microwave background, are so immense that only a few of them fit across our entire sky. This means our measurement of their properties is inherently uncertain. That strangely muted quadrupole, the quiet bass note of the universe, might not be a profound clue to the cosmos's shape. It might simply be the way our particular cosmic dice landed. The same logic applies to other large-scale anomalies. The hemispherical power asymmetry, where one half of the sky seems more vigorous than the other, could be a statistical fluke, a mere cosmic lopsidedness in our unique patch. We are like sailors on a vast, foggy ocean, trying to map the entire sea from the single wave our ship is riding. We can measure the properties of our wave with incredible accuracy, but we can never be sure if it is a typical wave or a gigantic outlier. This cosmic variance is not a flaw in our experiments or our math. It is a fundamental property of our existence. We are trapped within a single universe, trying to deduce the rules that generated it from the one and only outcome we will ever see. It forces a humbling question upon every grand discovery we make. When we find a strange feature in the ancient light, are we reading a message from the dawn of time, or are we just staring at our own unique and perhaps unrepresentative cosmic fingerprint? This grand inflationary paradigm, for all its explanatory power, rests upon a ghost. The inflatoned field remains one of the most successful ideas in cosmology that we have never directly detected. We see its immense shadow cast across the cosmos in the form of a flat, uniform universe, but the field itself has vanished without a trace. So what was it? The leading idea is that it was a scalar field, a kind of energy that permeated every point in space, possessing a specific potential energy landscape. Imagine a ball resting high up on a perfectly flat but gently sloping hill. That high energy state, that false vacuum, is what drove the exponential expansion. The universe was trapped in this meta-stable condition, and the energy density of this false vacuum had a repulsive gravitational effect, causing space to stretch at a ferocious exponential rate. But this state was not forever. Just as a ball can eventually roll down a hill, the inflatoned field tunneled or slowly rolled down its potential energy slope. As it rolled, it began to oscillate at the bottom of that hill, and those oscillations converted the immense energy of the field into a hot, dense soup of particles and radiation, effectively igniting the Big Bang as we traditionally think of it. This moment, known as reheating, is when the universe truly turned on. The cosmic microwave background provides our tightest constraints on this entire process. The exquisite flatness and the specific pattern of the primordial ripples tell us the inflaton must have rolled slowly, and that its potential energy hill must have had a very particular shape to produce the spectral index we observe. Yet for all these constraints, we are still describing the ghost by the shape of its shadow. We have no idea what the inflatoned field actually was in terms of fundamental physics. Is it a cousin to the Higgs field? Is it a manifestation of gravity itself, or something entirely new, a particle or force that faded from existence after its one monumental task was complete? The central mystery is not just what it was, but why it behaved the way it did. Why did inflation start in the first place? What set that initial condition, that ball on the hill? And even more puzzling, why did it stop? The graceful exit from inflation is as crucial as its beginning, for a universe that inflates eternally would remain a barren, empty void. The start and stop mechanisms are completely unknown, hidden behind the very wall of opacity that inflation itself created. We are left with a breathtakingly successful model that explains so much, yet its core engine, the inflaton, remains a placeholder for a deeper truth we have not yet uncovered. The CMB is the final report from that epoch, a document we can read perfectly, but whose author remains a complete and total mystery. That frozen symphony of creation left its echo not just in the ancient light, but in the very architecture of the cosmos we see today. This is the story of Barrian acoustic oscillations, a cosmic rhythm imprinted on both the infant universe and its adult form. In the first 400,000 years, the universe was a seething plasma, a tight coupling of light and matter where gravity was constantly trying to pull particles together, while the intense pressure of radiation was pushing them apart. This created a relentless tug of war, generating powerful sound waves that rippled through the primordial fluid. These were not gentle waves, but the loudest sonic booms in all of existence, traveling at over half the speed of light. Then, in an instant, everything changed. When the universe cooled enough for atoms to form, the light decoupled from matter and streamed freely across space. That light became the cosmic microwave background, and in its temperature patterns, we see a snapshot of those sound waves frozen in time. The most common distance a sound wave could travel before that moment became a cosmic ruler, a standard measuring stick etched into the fabric of reality. This distance manifests as a distinct preferred scale in the CMB, a specific size where the hot and cold spots are most likely to be found, but the story does not end there. That same acoustic scale was also frozen into the distribution of matter. The ripples that were moving outward through the plasma left a faint spherical shell of slightly higher density around every primordial over density. Think of it like a cosmic fingerprint where every initial lump is surrounded by a faint circular ridge. For billions of years, gravity amplified these patterns. The central overdensities collapsed to form the cores of galaxy clusters, while that surrounding spherical shell, that fossilized sound wave, became a preferred distance at which we find galaxies today. When we map the universe in 3 dimensions, we see that galaxies are more likely to be separated by this specific distance, about 500 million light-years, than any other. It is the ghost of that primordial sound, still echoing in the vast voids between galaxies. The cosmic microwave background gives us the pure, initial measurement of this ruler, while the modern galaxy maps show us how it has stretched over time. By comparing the two, we get one of the most powerful and direct measurements of the universe's expansion history. It is a crucial cross-check, an independent confirmation of the dark energy and cosmic acceleration we see from other methods. Yet, the full journey of these oscillations is a tale of incredible complexity. The simple sound waves in the plasma were soon complicated by the relentless pull of dark matter, which began sculpting the cosmos long before the ordinary matter could even move. The story written in the galaxies is a layered narrative, a collaboration between the clear, sharp signal from the dawn of time and the invisible, gravitational hand that has been shaping everything ever since. Beyond the brilliant glow of the cosmic microwave background lies a far more elusive and ancient fossil, a whisper from a time when the universe was just 1 second old. This is the cosmic neutrino background, a vast sea of ghostly particles that outnumbers the atoms in the cosmos by over 1 billion to 1. These are not the neutrinos we detect from the Sun or from distant supernova, which are energetic and relatively new. These are the primordial ones, the cooled remnants from the era when the universe was dense and hot enough to keep them constantly interacting with the soup of creation. When the cosmos was about 1 second old, it expanded and cooled to the point that these neutrinos ceased to scatter off other particles. They decoupled, flying freely through space, and have been traveling nearly undisturbed for the entire 13.8 billion year history of the universe. While the CMB shows us the universe at 400,000 years, the cosmic neutrino background would give us a direct snapshot from its first second, a view into a hotter, denser, and far more violent epoch. The challenge, however, is almost beyond comprehension. These primordial neutrinos have been stretched and cooled by the expansion of the universe to an energy so low that they barely interact with anything. They stream through you, through the entire Earth, and through our most sensitive detectors as if they were not even there. Catching one would be like trying to hear a single snowflake land in the middle of a roaring hurricane. Yet, if we could somehow measure this background, it would revolutionize our understanding. The cosmic neutrino background would provide an independent and far earlier measure of the universe's conditions. It would tell us the exact temperature of the cosmos at 1 second old, providing a critical test for our models of Big Bang nucleosynthesis. It could even reveal if neutrinos have unexpected properties, like a much larger magnetic moment that would have left an imprint on their distribution. Most importantly, because these neutrinos were traveling at nearly the speed of light when they decoupled, they would have had a dramatic smoothing effect on the very small-scale ripples in the matter distribution. Detecting their subtle gravitational influence would be like finding the signature of a ghost that helped sculpt the cosmos before the first light had even been born. This ultimate cosmic fossil remains just beyond our grasp, a silent chorus from the universe's very first breath, holding secrets we are only beginning to dream of uncovering. Yet even the universe's first recipe was not cooked to perfection. The cosmic microwave background sets an immaculate table for the creation of the first elements, providing the precise temperature and density that should have produced a specific, predictable amount of lithium-7. Our models, calibrated by the CMB's pristine data, tell us exactly how much of this light metal should have been forged in the Big Bang's nuclear furnace. But when we look out at the oldest stars in our galaxy, the ones that formed from nearly pure primordial material, we find a glaring discrepancy. These ancient stellar fossils contain only about 1/3 of the lithium that our theories insist should be there. This is the lithium problem, a stubborn crack in our otherwise successful story of cosmic dawn. It is not a small statistical error. It is a factor of 3 difference that has persisted for decades, defying every attempt to explain it away. Perhaps nuclear reaction rates in the early universe were different than we have calculated in our laboratories. Or maybe unknown particles, like a certain type of dark matter, were present during those first few minutes, decaying or interacting in a way that destroyed lithium as quickly as it formed. The lithium problem is a quiet but persistent alarm bell, telling us that our picture of the first 3 minutes is still incomplete. And if our understanding of Big Bang nucleosynthesis is flawed, then the initial conditions we derive from the CMB for the entire cosmos might also need a subtle but profound adjustment. The very same exotic physics that consumed the primordial lithium could have left its own faint, as yet unseen, signature on the cosmic microwave background itself, perhaps in a slight distortion of its spectrum or a minute twist in its polarization. The missing lithium is more than a chemical curiosity. It is a ghost from the nuclear dawn, pointing toward a deeper layer of physics that we have only just begun to glimpse. The silent geometry of the cosmos points to a hidden master. The cosmic microwave background's exquisite flatness and the specific pattern of its acoustic peaks do more than just tell us about the universe's shape. They act as a cosmic scale, precisely weighing all the components of reality. When we add up everything we can account for, the ordinary matter for stars and planets, and the cold dark matter that sculpts the galaxies, the ledger does not balance. The total falls dramatically short of what is needed to create the flat universe we observe. There is a missing energy, a vast, dominant component that makes up about 70% of the entire cosmos. This is the ghost in the machine, dark energy. The CMB does not see dark energy directly, but it feels its gravitational absence. To fit the pristine data from the ancient light, our models must include this mysterious force with a very specific and bizarre property, a strong negative pressure. Think of positive pressure as the force you feel when you push against a wall. It resists you. Negative pressure is the opposite, a sort of cosmic tension, like a stretched rubber sheet that wants to pull inward. But dark energy's negative pressure does the reverse. It causes a gravitational repulsion, pushing space itself apart. The CMB reveals that this strange, repulsive energy must have been lying dormant for billions of years, its effects negligible while gravity pulled matter together to form galaxies. Then, as the universe expanded and matter diluted, dark energy's constant density allowed it to eventually dominate, taking command of cosmic evolution and beginning the era of accelerated expansion we see today. Why did this transition happen precisely when it did, allowing for a long, fertile period for galaxy and life formation before the great cosmic rip began? The ancient light provides the undeniable evidence that this mysterious force exists, but its origin remains the most profound puzzle in physics. Is it the immutable energy of the vacuum itself, or a dynamic field that has slowly awakened over cosmic time? The CMB gives us the answer sheet, showing us that the equation of the universe requires this dark term, but it refuses to show its work. Gravity's lens appears to be focusing a little too sharply. Among the many subtle whispers within the cosmic microwave background, one persistent signal suggests that the gravitational lensing of this ancient light is slightly more pronounced than our standard cosmic model allows. Scientists call this the L anomaly, where a L is a parameter that should equal 1 if our understanding is perfect. Instead, multiple analyses point to a value just a little bit greater, a subtle but stubborn excess. It is as if the cosmic lenses, the vast clouds of dark matter that warp the light's journey, are slightly stronger than we predicted. This is not a dramatic crack in the foundation, but a hairline fracture that demands an explanation. The first and most conservative possibility is that this is simply a statistical fluke. We are dealing with an incredibly faint signal buried in a sea of noise, and sometimes random fluctuations can conspire to mimic a coherent effect. Perhaps our single universe, by pure chance, has a lensing amplitude that sits on the high end of the probability curve, a cosmic roll of the dice that looks meaningful but is ultimately just luck. The second possibility is a systematic error, a subtle flaw in how we process the immense datasets. The measurement of lensing in the CMB is a monumental achievement in statistical inference. We are not seeing individual bent rays of light, but detecting a collective smearing of the primordial patterns. This requires incredibly complex algorithms to tease the signal from the noise. If there is a tiny, unaccounted-for bias in our method, perhaps from residual foreground light or an incomplete model of the telescope's own behavior, it could artificially amplify the perceived lensing signal. We might be seeing the ghost of our own analysis, not a true feature of the cosmos. But if the anomaly is real, its implications are profound. A stronger than expected lensing signal means that matter, particularly dark matter, clumped together more efficiently than our models predict. Something may have given gravity an extra helping hand in the universe's middle age, enhancing the growth of cosmic structure. What could provide this boost? One thrilling possibility involves the ghostly neutrinos. If the lightest of these particles has a slightly larger mass than we currently think, its gravitational influence would be more significant, pulling matter together more effectively as it slowed from its relativistic speeds. Another, more radical idea points to the nature of dark energy itself. Perhaps it is not a constant vacuum energy, but a dynamic field that has evolved over time. Certain models allow for an early interaction between dark energy and dark matter, a brief coupling that could have pumped extra energy into the gravitational collapse of structures, leaving a stronger lensing imprint on the CMB. The eerily anomaly sits in a tantalizing gray zone, a persistent whisper that is too faint to claim as discovery, yet too consistent to ignore. It challenges us to look deeper, to question whether our map of the cosmic ingredients is truly complete, or if an unseen hand once gave the universe's invisible skeleton a little extra strength. The most obvious feature on the map of the ancient universe is our own motion. Across the sky stretches a vast temperature dipole, a colossal hotspot in one direction and an equally immense cold spot directly opposite. This is the CMB dipole, and it reveals we are not sitting still. Our entire solar system is racing through the cosmos at over 600,000 miles per hour, plunging toward the constellation Leo. As we move, we plow through the sea of primordial photons. Ahead of us, the light is squeezed, blue-shifted into a slightly warmer glow. Behind us, it is stretched, redshifted into a deeper chill. This Doppler effect is the primary reason for the dipole, a cosmic speedometer showing our local velocity. But this simple explanation opens a far deeper mystery. What immense gravitational force is pulling us so insistently in one particular direction? Our motion is not just the sun orbiting the galaxy, it is the entire galaxy and our entire local group of galaxies being tugged on a truly cosmic scale. This peculiar velocity points toward a vast, unseen concentration of mass, a gravitational landmark so enormous it can command the motion of countless galaxies. We call this the Great Attractor, a region of space obscured by the dust of our own Milky Way, hiding a supercluster of galaxies with a gravitational pull powerful enough to draw us in. Yet even this may not be the whole story. The puzzle deepens when we trace this river of galaxies further. Our local flow appears to be part of a much larger current, all moving toward an even more massive and distant structure known as the Shapley supercluster, the greatest concentration of matter in our observable universe. It is a staggering thought that the subtle pattern in the oldest light can reveal not just our speed, but the ghostly outline of the largest cosmic structures whose collective gravity is steering us through the void. But the most revolutionary possibility is that this motion is not the entire answer. Could a tiny fraction of this dipole be intrinsic, a genuine lopsidedness baked into the universe at its birth? If even a small part of this hot and cold pattern was primordial, it would shatter the cosmological principle, the foundational idea that the universe is homogeneous and isotropic. It would mean the Big Bang itself was not perfectly symmetrical, that the initial fire had a preferred direction, a fundamental tilt to reality. The hunt is on to disentangle our local motion from any possible intrinsic dipole. Future missions plan to use distant quasars or gravitational waves as a fixed reference frame, a stationary background against which to measure our true speed. If they find a discrepancy, if the CMB dipole is even slightly larger than our motion can explain, it would be one of the most profound discoveries in cosmology. We would have to accept that the universe has a handedness, a fundamental asymmetry written into its first light, challenging our very understanding of how everything began. This breathtakingly simple model, known as lambda cold dark matter, stands as the single most successful theory in the history of cosmology. With just 6 basic numbers, it can describe the entire evolution of our universe, from its first whisper in the cosmic microwave background to the vast galactic empires we see today. It tells you the amount of ordinary matter, the quantity of dark matter, the age of the cosmos, the amplitude of the initial seeds, their spectral tilt, and the strength of dark energy. With these 6 parameters, you can run the entire 14 billion-year cosmic film, and what unfolds on the screen matches our reality with stunning, almost unbelievable precision. This is a mystery as deep as any anomaly, the shocking effectiveness of a simple key unlocking the entire cosmos. Why should a system of such staggering complexity be so elegantly described by so few ingredients? It is as if you were given a box containing every symphony ever written, every painting ever painted, and every book ever authored, and you discovered that all of it could be recreated by combining just 6 fundamental notes. The success of this model is a profound clue that we are on the right track, that we have grasped the universe's fundamental architecture. Yet, its very simplicity is also deeply suspicious. Does this elegant model work because it is true, or because it is a magnificent approximation, a beautifully simple story that hides a far more convoluted and strange reality? Every one of the 50 mysteries we have explored is a tiny crack in this simple facade, a hint that the 6 parameters are not the whole story. The Hubble tension, the anomalous quadrupole, the lithium problem, each one is a quiet but persistent signal that our beautifully simple map might be missing a few crucial landmarks. Perhaps dark energy is not a simple constant but a dynamic field with a history of its own. Perhaps dark matter is not perfectly cold and sluggish, but has a tiny bit of warmth that changes how galaxies form. The incredible success of the lambda cold dark matter model is not the end of the journey, but a signpost pointing toward an even deeper layer of truth. Its 6 numbers are the universe's way of giving us the broad strokes, a sketch so accurate we mistook it for the final masterpiece. But the real painting, it seems, is filled with subtle, ghostly details we are only just beginning to see. This quest for whispers from the dawn of time is far from over. The next generation of cosmic listeners is already under construction. Instruments of such staggering sensitivity, they will hear the ancient light in ways we can barely conceive. Projects like the Simons Observatory and the ambitious CMB S4 consortium represent a quantum leap in our observational power. These are not merely incremental upgrades, they are entirely new senses for humanity, arrays of hundreds of thousands of detectors perched in the high, dry deserts of Chile, scanning the sky with a resolution and precision that dwarfs all previous efforts combined. Their goal is to measure the faint polarization of the cosmic microwave background with an error margin so small it borders on the absurd. They are hunting for the ghost of a ghost, the faint swirling pattern of primordial gravitational waves, the B-mode signal that has eluded us for so long. This is the definitive test, the moment of truth for our story of cosmic inflation. A clear detection would be a triumph, a direct confirmation that the universe was indeed stretched by a ferocious, hyper-fast expansion in its first instant. It would crown our standard model of cosmology and open a new window into the quantum nature of gravity itself. But what if they find nothing? The profound and terrifying possibility is that these magnificent machines, with all their unprecedented power, still hear only silence. A continued null result, a universe stubbornly refusing to reveal its gravitational wave background, would trigger a crisis far deeper than the Hubble tension. It would force a radical rethink of inflation itself. Perhaps the process was much gentler and occurred at a far lower energy than our favorite theories predict. Or perhaps inflation never happened at all, and we must search for an entirely new explanation for the universe's smoothness and flatness, a Genesis story we have not yet even dreamed of. These future observatories will not just answer old questions, they will undoubtedly uncover new anomalies, strange features in the primordial tapestry too faint for our current eyes to see. They might finally resolve the puzzle of the hemispherical asymmetry or prove whether the cold spot is a statistical fluke or a cosmic bruise. With each order of magnitude improvement in sensitivity, we peel back another layer of the cosmic onion, knowing that the core might hold not a simple truth but a deeper, more beautiful mystery. This two-dimensional screen of ancient light holds a final, humbling secret. There is a fundamental limit to how much we can ever learn from it, a cosmic information barrier. The surface of last scattering is like a distant painted curtain, and we are the audience in a fixed seat, forever unable to see behind it or view it from another angle. Every photon, every temperature fluctuation, every subtle polarization we measure is a single data point from this one and only cosmic snapshot. This creates a hard ceiling on our knowledge, a statistical uncertainty known as the cosmic variance limit. For the very largest scales, the broadest waves in the cosmic tapestry, the problem is most acute. Only a handful of these immense patterns can fit across our entire observable sky. This means our measurement of their properties is inherently uncertain. We are like someone trying to understand the entire concept of weather by studying a single, solitary cloud. That cloud might be a perfect, fluffy cumulus, or it might be a rare and strange formation. From our one sample, we can never be sure. The quiet of the quadrupole, the lopsidedness of the hemispheres, these could be profound cosmic truths, or they could simply be the unique statistical fingerprint of our particular pocket of the universe. We are trying to deduce the entire recipe of reality from a single slice of the cosmic cake. So, are we approaching this ultimate information wall? Have we squeezed nearly every secret we can from this ancient glow? The answer is a thrilling no. While we may be nearing the theoretical limit for the temperature map alone, the true frontier lies in polarization, the subtle directional whisper of the light. This is a whole new channel of information, a different language spoken by the same primordial event. By combining temperature and polarization with ever more exquisite precision, we can cross-check our findings and beat down the uncertainty. Furthermore, our ability to model and subtract foregrounds from galactic dust to distant clusters is a form of informational alchemy. We are learning to separate the cosmic signal from the noise with such skill that we effectively create a clearer, higher-resolution image from the same raw data. The limit is not a brick wall, but a horizon we are learning to see beyond. The real question is not if we will hit a ceiling, but whether our own creativity can keep pace with the universe's subtlety. The oldest light may have given up its easiest secrets, but its deepest truths are waiting for a generation of thinkers with new questions and new ways to listen. This ability to read the universe's birth certificate is itself a staggering fact. We are collections of atoms forged in the hearts of long-dead stars, and yet we can point our machines at the sky and decode the very first chapter of cosmic history. The cosmic microwave background is not just a map of the past, it is a mirror reflecting our own profound capacity to understand. How is it that the human mind, a product of this late and local cosmic evolution, can grasp the fundamental laws that govern the fiery beginning of everything? This is a mystery that transcends physics and ventures into the realm of philosophy. The equations we write down, the models we build, they resonate with the deep structure of the universe itself. It is as if the cosmos is not only comprehensible, but in some deep sense waiting to be understood. This intelligibility is a gift with no clear explanation, a silent agreement between our minds and the nature of reality. And within that gift lies an even more provocative clue, the apparent fine-tuning of the cosmos for life. The properties of the CMB are a ledger of this delicate balance. If the initial expansion rate had been a fraction faster, the universe would have flown apart before any structure could form. A fraction slower, and it would have collapsed back in on itself. If the strength of the primordial ripples had been slightly weaker, gravity would never have gathered the gas to form galaxies and stars. Slightly stronger, and matter would have clumped into monstrous black holes. The CMB reveals a universe that is not just habitable but improbably, exquisitely tuned for habitability. So what are we to make of this? Does this precise calibration point toward a deeper purpose, or is it merely a cosmic selection effect? One compelling answer lies in the multiverse. If our universe is just one bubble in an infinite froth of universes, each with its own random set of physical constants, then there is no mystery. We simply find ourselves in one of the rare bubbles where the numbers accidentally allow for galaxies, stars, planets, and life to emerge. In this view, the fine-tuning is an illusion of our own location, a cosmic version of a lottery winner marveling at their own luck. But another possibility is that the fine-tuning is a fundamental feature of reality, that the laws of physics are uniquely set up to allow for the emergence of complexity and consciousness. This does not necessarily point to a creator, but it does force us to consider that life and mind might be a natural, and perhaps even an intended, outcome of the cosmic recipe. The cold, hard data of the CMB, a relic of the Big Bang, leads us directly to the warm, living question of our own existence. Are we a happy accident in a vast and indifferent multiverse, or are we an expression of a cosmos that is, in its very foundations, leaning toward life? The oldest light does not provide an answer, but it illuminates the question with a clarity that is both humbling and awe-inspiring. Our quest to decode the ancient light ultimately forces us to confront the very nature of reality's fabric. The deepest anomalies in the cosmic microwave background might be whispers from a realm where the universe is not made of point-like particles, but of tiny, vibrating strings. This is the domain of string theory, a framework that suggests the fundamental constituents of reality are unimaginably small loops and strands, oscillating in many more dimensions than the three of space and one of time we experience. The connection to the vast, cold CMB is not as distant as it seems. Specific models of inflation built within string theory, such as brane inflation, propose that our universe is a three-dimensional membrane or brane floating in a higher dimensional space. In this picture, the violent expansion of inflation could have been triggered by the collision of our brain with another. Such a collision would not have been a gentle kiss, but a cataclysmic event that released immense energy and, crucially, would have produced a specific non-Gaussian signature in the primordial ripples. It would have left a distinct statistical fingerprint on the CMB, a subtle preference for certain triangular configurations of hot and cold spots that pure randomness cannot explain. This is the kind of ghostly correlation that next-generation telescopes are desperately searching for. Furthermore, the extra dimensions required by string theory are not simply passive. Their shape and size, a concept known as the compactification manifold, determine the properties of the particles and forces in our observable world. The process of compactifying these extra dimensions from the initial hot chaos of the Big Bang could have left its own scars. It might have broken fundamental symmetries on a cosmic scale, imprinting a specific handedness or parity violation across the entire sky. That strange, large-scale preference for one type of spiral pattern in the CMB could be the faded echo of the universe choosing how to fold away its hidden dimensions. The most profound link lies in the nature of the inflaton field itself. In string theory, the inflaton is not a ghost, but could be a concrete object, like the distance between two branes or the vibration of a string across a curled-up dimension. The specific shape of its potential energy hill, which dictated the spectral index and the strength of the gravitational waves, is no longer an arbitrary guess, but is derived from the intricate geometry of the theory's hidden landscape. This offers a potential explanation for why our universe has its particular set of 6 numbers. They are the unique outcome of one particular way for the extra dimensions to stabilize. String theory connects the impossibly small to the astronomically large, suggesting that the grand architecture of the cosmic microwave background, with all its puzzling features, was woven by the vibrations of entities a billion times smaller than an atomic nucleus. Finding even a hint of these theoretical signatures would be more than just confirming a model of inflation. It would be our first empirical glimpse into the multidimensional architecture of all existence, revealing that the oldest light in the sky is a reflection of the universe's deepest, most hidden strings. This ancient light, which tells us so much about our beginning, also holds a detailed prophecy for our end. The precise recipe of the cosmos, meticulously weighed by the cosmic microwave background, spells out a very specific destiny. With dark energy dominating and the density of matter relentlessly thinning, the expansion of space will continue forever, accelerating into an endless cooling drift. This is the cosmic endgame known as the heat death. It is not a dramatic explosion or a violent collapse, but a slow, quiet fading of all activity. Imagine a campfire on a vast, dark plain, its last embers glowing. One by one, those embers wink out, not with a bang, but with a sigh, until only a uniform, pervasive cold remains. In this distant future, trillions of years from now, the last stars will have long since burned out. Galaxies will have evaporated as their stars either die or drift away into the expanding blackness. Even the black holes, the universe's most tenacious anchors, will slowly evaporate through Hawking radiation, vanishing in a final, faint puff of particles. The cosmos will be a thin, ever-cooling soup of fundamental particles and radiation, so widely dispersed that a single photon might travel for eons without ever encountering another particle. The universe will become a static, eternal grave, where the concept of time loses all meaning because nothing ever changes and nothing ever happens again. The data from the CMB makes this outcome seem almost inevitable, a direct consequence of the dark energy it helped to discover. Yet the true mystery here is not a scientific one, it is a deeply human puzzle. How do we, conscious beings born in a brief, vibrant spring of cosmic history, reconcile our existence with this silent, frozen eternity? Our lives, our civilizations, and all of art and discovery will have been a fleeting spark in an unimaginably long and dark night. This can feel like the ultimate exercise in futility, a story that builds to a magnificent middle only to conclude with an irreversible, featureless fade to black. But perhaps this very bleakness forces a profound shift in perspective. If the universe's final act is fixed, then the entire meaning of the cosmic story must reside in its middle chapters, in the temporary, brilliant flare of complexity that we are a part of right now. The heat death does not erase the reality of galaxies, stars, planets, and life. It makes them all the more precious. They are not failed attempts at permanence, but magnificent, transient achievements against impossible odds. The silence of our cosmic end does not negate the music we are making now. It amplifies its beauty, reminding us that meaning is not found in the final page of the book, but in the story itself, a story written in the afterglow of creation and illuminated by the brief, wonderful light of consciousness. From the silent axis of evil to the ghostly whispers of B-modes, we have journeyed through 50 profound secrets locked within this ancient glow. The cosmic microwave background is far more than a faded photograph of the infant universe. It is a living, breathing document. Its large-scale anomalies challenge our deepest assumptions of a uniform cosmos, while the fine, polarized details in its light probe the very quantum nature of gravity. Every time we build a better telescope, every time we refine our models, this primordial canvas reveals a new layer of subtlety, a fresh mystery that pushes the boundaries of our understanding. This is not a puzzle we are close to finishing. It is a frontier we are only just beginning to map. So keep looking up and keep wondering. The next revolutionary insight into the nature of reality is almost certainly encoded in that faint, cold light from the beginning of everything, waiting for the next curious mind to finally decode its message. That persistent static in their radio telescope was more than just an annoyance. For Arno Penzias and Robert Wilson, it was a mystery they could not eliminate. They scrubbed the giant horn antenna, chased away a pair of nesting pigeons, and still the faint, uniform hiss remained, a whisper from every direction in the sky. They had no idea they were listening to the cooled remnant of creation itself, the echo of the Big Bang. That moment of accidental discovery was not an ending but a beginning. It ignited a human adventure that continues to this day. It sent teams of scientists to the most extreme environments on Earth, to the high, dry plateaus of the Atacama Desert and the frigid, thin air of the South Pole, where the sky is at its most transparent. It inspired the launch of magnificent observatories into the silent void of space, satellites named COBE, WMAP, and Planck, each one a more sensitive ear tuned to the universe's first cry. This is not just a story of data and detectors. It is a story of human curiosity, of people dedicating their lives to understanding a faint, cold light that fills the void. They are the cartographers of creation, meticulously mapping a fossil older than every star, every galaxy, every atom. This grand endeavor connects the physicist in a clean room calibrating a sensor to the engineer braving Antarctic winds to service a telescope. It binds all of us to the cosmos in a profoundly meaningful way. The carbon in our bodies, the iron in our blood, was forged in stellar furnaces that themselves grew from those primordial ripples. We are not just observers of this ancient light, we are products of it. Our very existence is a temporary, conscious embodiment of the universe's long journey from a searing hot beginning to the structured beauty we see today. The quest to decode the cosmic microwave background is one of humanity's greatest adventures because it is, at its heart, the quest to understand our own origin story. We are the universe awakening, looking back at its own birth and trying to understand what it all means. And that makes every subtle anomaly, every whispered secret from the sky, a message meant specifically